Hi, I'm Alex Garcia, and thanks for joining us here at NTWC Live. It is a team effort between Bill Reed, Tim Smith, and I. We'd like to say thank you to a few groups that helped make this possible. It's USAA, South Padre Island Convention and Tourist Bureau, the Weather Company, and the Weather Boy. And now, here's Tim Smith.
Good morning, everybody. Welcome to NTWC Live for Wednesday, November the 16th. We are glad to have you all along with us this morning as we come to the almost end of the 2022 hurricane season. Just a couple more weeks and at least officially the season will be over. Who knows if we're done, but that is yet to be determined. Got a great program for you today. We try to keep you on the cutting edge of technology, and today is going to be one of those things where you really learn some really cool stuff that's happening and helping us observe not just hurricanes, but all kinds of weather in kind of a new and exciting way. Windborne Systems is with us. We'll get to that in just a second. We want to start, though, by thanking our sponsors who make these programs a reality. First and foremost, USAA. Boy, they have been with us from the very beginning with NTWC Live, the National Tropical Weather Conference, and all things that the Storm Science Network does. So thanks to USAA. The South Padre Island Convention and Visitors Bureau. South Padre Island, of course, is the host for the National Tropical Weather Conference. We'll be back there live again in April of 2023. Early registration is now open. You can find it on our Facebook page, on our website. Go to that and get registered so you can see us all in person, and we'll get to meet everybody and see some old friends again coming up in April of next year. The Weather Company, Weather Boy, Walmart, the City of Brownsville, Black Magic Design, the Port of Brownsville, all folks who help make these events a reality. So as we wind down the hurricane season, let's go to Bill Reed, former director of the National Hurricane Center, to talk about what's going on today. Bill, is there anything left out there?
Well, yeah, not looking out my window. We're in the 40s, north wind at 15, and gray skies. So we definitely transitioned up on the upper coast here to the more winter-like pattern that we see. Last week I was in Clearwater, and we had Nicole come through Florida then. So it's a reminder that the season really doesn't end till it ends. Some years we go beyond November. But I'll just do a couple of quick show me's here for the finish this off. And satellite imagery shows there's very quiet across the tropics, Gulf, Caribbean, pretty much dry air and shut down. Front is all the way through most of the Gulf now in the southern Gulf. This is a system being generated by a disturbance in the westerlies moving into the mid latitudes, and there's really nothing of any consequence there. Eastern Pacific season typically is over by now, the middle of November, and again, some convection on the convergence zone, but nothing really there. And everybody's favorite graphic, we live along the coast down here, nothing expected the next 5 days. So that brings us to today's show. As most of you have noticed over the years, the three of us strive to bring people smarter than us into the shop to talk about things that they know about that we can use in the broadcast world, educating the people that depend on us for weather information. Today we've outdone ourselves with our two guests from Windborne Systems. We have Todd Hutchinson. He is has a Master of Science degree in meteorology from Oklahoma and a bachelor's from State University of New York in Albany. He's the director of meteorology at Windborne. He has 25 years of experience in the commercial field, and prior to going to Windborne, he was manager of numerical weather prediction and radar application at IBM, the Weather Company. Very impressive job done there. And then we have Andrey Sushko, who's coming to, Todd is in Boston right now at home, and Andrey is out in Palo Alto where the company is located. Andrey has a PhD in experimental physics from Harvard and a bachelor's degree in theoretical physics and mathematics from Stanford. And his interest is in the technology end of it, and he's developed quite a system that they're going to talk about. I won't overdo that, but he is the founder of Windborne and currently serves as the CTO of the company. So Todd, I'll turn it over to you. Welcome.
Great, thank you, Bill. Appreciate that. I'm going to jump right in and
Todd, you muted when you took your screen full.
All right, can you hear me now?
Yeah, sir.
One more time, sorry about that.
Yeah, it's auto muting when you, there you go. Now you're good. Now you're good. No, no, still can't hear you.
Huh. Look for the little red circle over the microphone icon.
All right, well, will I work through, I think you can hear me now?
Todd, I can try sharing the screen and let you talk instead, if
That'd be
that
great, thank you.
works
Thank you,
better.
Andrey.
Let's try that.
All
There you
right,
go.
thanks, Andrey. And thanks, Bill, for that introduction. I guess we had one little technical thing that we'll resolve there, but I appreciate the introduction, and also I wanted to introduce you to Windborne Systems, company that's based in Palo Alto, California, and is about 3 years old now. The company itself is an outgrowth from Stanford University, where Andrey, who's on the call as well, and others within a group at Stanford actually began flying balloons in their undergraduate days in Stanford, and that developed into a company that currently is flying balloons, as is shown in this image here on my first screen. You can actually see a balloon up in the air there, well above the underlying terrain. That's actually a balloon that was launched from Svalbard, which is in the northern reaches of the Arctic, where we were involved in an Arctic field campaign over the last 2 years, and some really beautiful scenery up there for those in the company that were able to get up there. You can see that and actually launch the balloon. So let me just start very quickly and say what's different here. Why are we presenting this? If you're familiar with weather balloons themselves, you probably know that they're launched from various locations throughout the world every day. In the United States, they're launched from nearly 100 locations twice per day. And in the morning and evening, they fly, they go up, they eventually burst at about 35 kilometers, and then the remnants descend down, back down. The case that what we're talking about here is a different type of balloon. This balloon is actually going to fly for and go up and down many times over its lifetime. It will fly for days at a time, even up to weeks, and it'll fly occasionally for thousands and thousands of kilometers. Here's the details on it, and the balloon itself collects in situ observations, atmospheric observations, temperature, moisture, winds, and it collects this information as it flies through the atmosphere. As I mentioned, it's long duration and long range. It can last for orders of weeks, and it can cross long distances simply by flowing with the wind, by traveling with the wind. As the wind flows, the balloon travels along with it. Real-time full-range altitude control. What does that mean? That basically means that remotely we can tell the balloon to go up or down, and we can do this about 25 times per flight, all the way from the lower levels of the atmosphere up to higher levels of the atmosphere. And you can think about that as in the lowest 1 kilometer of the atmosphere, where down to about 500 meters, just not too far above the surface, all the way up to the levels of about 15 kilometers. And that's typically at jet stream or even higher levels than the jet stream. You can continue to go up and down. We'll show you some examples of that in just a minute. I'm going to turn it over to Andrey here so that he can describe a little bit more of the details of the data that's collected and the technical details of the system.
Thanks a lot, Todd, for that introduction. And I'm not going to go into the full nitty-gritty technical details of how this is set up, because that will take far too long and probably scare away half the audience. But the key things to note here is that when we talk about this kind of atmospheric sensing, we are developing a sensor package that is To a large extent similar to what radiosondes fly. We're using sensors that come from similar manufacturers, and the interesting part is really integrating it in a way that it's compatible with the kind of system that we're operating. So being able to collect data on ascents and on descents, both at reasonably high quality, quality that we've verified now across cumulative years of flight to perform quite well and up to the standard of radiosondes. But because we have this much longer endurance system, it unlocks a whole range of other things that we're able to do. So one of the straightforward ones is if you're paying for a similar amount of hardware to a radiosonde, but you're now collecting 30 profiles, 40 profiles in a flight instead of 1 or potentially 2 for the ascent and descent sondes, you're now amortizing the hardware cost over a lot more profiles, which makes it considerably more cost effective for upper air observation. The other thing that Todd mentioned is because we can fly for a long time, record is now past 2 weeks at this point, you can cover a long distance, and we'll have some fun slides on that later, but what that means is that this provides a platform for data collection, not just near the launch site, and expressly very far away from the launch site, and we'll talk more about that later, I'm sure. But one of the main guiding design philosophies in this hardware development has been how do we make a system that is long endurance, high performance, high controllability, but also very cheap. And this very cheap comes in when you're designing normal radiosondes because you're not getting most of them back after you launch it. And in our case, we're following a similar design philosophy, but trying to improve the amount of data collection by 1 or 2 orders of magnitude, while still keeping very small, very lightweight, very cost-effective hardware. And so a lot of the development between 2015, when this project was started as a student project, and now has been on how do we make the hardware smaller, how do we make the hardware lighter, how do we make the hardware perform well while being as simple as possible, essentially. And if you look at just the weight of all of the systems required to keep it running, I think our first flight, it was something like 3 kilograms. Right now, what we fly with the avionics package is around 300 grams. So there's, over that time, been an order of magnitude decrease in how much all of the systems required to keep it functional in the air now weigh. And as Todd mentioned, we've been doing a lot of flights of these. We consider this technology at a readiness level of 8, where the only real difference, if you look at the NOAA levels between 8 and 9, is that 9 requires operational adoption into the data collection system. And so we're working through trying to get this data. I'm sure Todd will discuss that further. But the basic balloon technology and the sensor technology, we now see as in a pretty high state of readiness. If we go over to the next slide, which I have control over, I realize. One thing that I like to just touch on is this concept of operations. As I mentioned, this is a system that has the ability to go up and down repeatedly and in a very controllable way. Typically, when we think about long-duration balloons, and there have been a lot of other experiments with long-duration balloons, there were some programs done with NOAA and NASA dating back to the 70s, I believe. But most of those were using so-called superpressure balloon systems, which are buoyantly stabilized. So the idea is you have a balloon with a fixed volume. It will rise up until the point where that volume is fully inflated. And once that happens, it has no more room to expand. And so just by buoyancy, it will then find the level at which it displaces its own weight, now that the volume is fixed, and it will sit there. And that way it can sit there for weeks, if you make it very non-leaky, for months at a time. I think the amateur record is something like a year using a literal foil party balloon that happened to be very not leaky. But these systems don't have significant controllability. There are ways to trim their altitude. Systems like Google Loon, which tried to do balloon-based telecoms, had these systems that allow you to adjust the altitude within a few kilometer range. But it's fundamentally existing in a stable equilibrium with small modifications. What we do is very different. We operate in an unstable equilibrium the vast majority of the time. What that means is that we don't have any feedback, and so if you start falling, you'll continue falling. If you start rising, you'll continue rising until you hit something. On the ascent, what you hit is your altitude ceiling, similar to a superpressure balloon, and as long as you hit it gently enough, that's okay. When you're falling, you generally don't end up with an okay scenario when you hit something, and so that's where the system has to act in order to turn around. But the way that the controller essentially works is it allows these transitions and it decides when you want to turn around. And that's configured through a lot of systems that we might touch on later. But the point is that those turnaround points are entirely flexible. We can choose them to be at any altitude between right below the ceiling all the way down to right above the surface. And so here's an example of a flight profile for those who can see the slides. The yellow line is real flight data of altitude versus time. And you can see these aren't just random transitions. We are at all points choosing when to turn around, and that decision is based on what data do we want to collect and which regions of the atmosphere do we want to be in for navigation, because winds have different directions at different altitudes, so we can constrict ourselves to a range, say, between 5 and 10 kilometers that might be more due east versus going down to lower altitudes that might be more due south, for instance. And that gives a decent degree of controllability to these flights. Yeah, Todd, I think I'll hand back over to you, but that's just a bit of high level on how we do these things.
Great, thanks, Andrey. Let's go on to the next slide, and we'll continue here. So where we've introduced the balloon system here, we're obviously in a tropical podcast, but we want to introduce that and then take you to where this balloon was used in the podcast. But by showing examples here, you can imagine what different things we can do. And this is a great example of a flight of a balloon system, of a balloon that actually circumnavigated the world. We launched a balloon from South Korea as part of a program that we were involved in February of this year. The balloon was launched from South Korea, traveled eastward with the winds that generally flow from west to east around the world, and continued. It took 16 days for this period of time for this balloon to track across the world. But there were some interesting things that went along. Now, I'm choosing one of one of the optimal cases of the balloons that had flown. They certainly don't all fly for this distance, but generally they're flying for many days and also long distances. A couple things occurred. Andrey mentioned a little bit about flying at different levels to take advantage of varying winds. If you think about how winds may vary from the surface up to high levels in the atmosphere, there can be lots of turning of the winds and changes in speed of the winds as you look at those different levels. And by directing the balloon through its control to the levels where the balloon can be propelled to areas that you're interested in observing, taking atmospheric measurements in, we can really guide the balloon to different locations. That may be one example of why you want to guide the balloon. This particular case, we happen to be flying across the world and into Europe, and we, at the time, did not, it was the early stages of the conflict going on in the Ukraine. We did not want to fly over that part of the world, so we were able to descend the balloon to lower levels where winds were more from the north and propel it farther south and avoid that region. So one example here, a tangible example of how we can navigate. But lots more examples, and you'll see more when we get into the tropics in just a minute. So we can go ahead one slide, Andrey. And in the similar way that Andrey showed the vertical profile earlier, this is the actual one from the flight above. That what we did was we flew through the Pacific Ocean. These vertical profile lines on the left here, the balloon was directed to fly up and down over the Pacific Ocean to collect valuable atmospheric data. as part of the campaign that was going on there. If you're familiar with large West Coast storms that often are associated with atmospheric rivers that bring moisture into the western United States, that was the program that was going on, where aircraft were flying within these flows of moisture in the Pacific Ocean, the atmospheric rivers. We were flying the balloons to collect data along with them and directing the balloons to fly up and down to collect vertical profiles such that we could collect data throughout many levels of the atmosphere and hopefully have more value by collecting those large profiles rather than simply remaining at levels. The nice thing, though, is even after across the Pacific, we're able to maintain at high altitude what we call cruise mode and essentially take advantage of the very strong jet stream level winds to propagate far across different parts of the world. As I mentioned before, we avoided the Ukraine by dropping to lower levels, as was shown here in this case, and that was remotely directed. One thing that probably maybe is implied so far but hasn't been stated is that these balloons can fly anywhere in the world and be remotely directed simply by communication through the satellite communications that are available today. And so a lot of things have brought this capability to fruition now. One is the communication, along with many of the things that Andrey and the rest of the team have developed in terms of the technology of the balloon. So if we can go forward one slide here. This picture here is actually just the paths of all the balloons that Windborne Systems has flown over the past 3 years while it's been incorporated as a company. If you were to count those lines, you'd actually count 500 different lines where balloons have flown during the lifetime. You can see just in this this slide where everything is thrown together into one image that there are various launch points, and they are at where the lines converge. One example I'm pointing to, I probably can't see, but in northern Alaska, where we were launching from near Barrow, Alaska, balloons were propagating eastward from Alaska, and that was, again, part of an Arctic campaign. But you can see other source locations as well, such as Svalbard in the north, South Korea, as well as southern Alaska and Hawaii, if you look close, and then the tropics, which is really what we're going to get into next, and looking into the tropical Atlantic. One thing you might notice is that the lines might be just a bit shorter in the Atlantic than they are in the northern latitudes, even given the variation with this projection. And one reason for that, of course, is because the atmospheric flow is stronger in the mid-latitudes, the further north latitudes, than it is in the tropical atmosphere. So why don't we go ahead one slide, and we'll show some examples there. I can go ahead to the next slide here. I zoomed in on that map that I just showed, except only showing the tropics here, and you can see what we did in this past summer. So during the 2022 tropical season, beginning about August 1st, in our case, we were launching these weather balloons, these Windborne balloons, from 3 different locations in the tropics. One was from Cabo Verde in the eastern Atlantic. A second was from Puerto Rico in the central or western, in the Caribbean, the western Atlantic, as well as several from northern Florida. The goal of the program was to collect atmospheric data near and perhaps in tropical cyclones, but especially in the environment surrounding tropical cyclones, such that the data could be collected and ultimately demonstrate how it could be fed into numerical weather prediction models and hopefully influence and improve the forecasts that are generated by weather prediction models by adding additional data to the initialization of those weather models. So during that period, we collected data. We flew 85 balloons and collected data throughout the Atlantic with these different source locations. And if we go on to the next slide, you can see that we did get into some interesting areas. One here is Hurricane Ian. Hurricane Ian, as I'm sure everybody on the call knows, was traveling northeastward towards Florida, after making initial landfall in Florida, it crossed the peninsula and back into the Atlantic Ocean just east of Cape Canaveral. The system there was, as it circulated and crossed Florida, we were launching balloons from northern Florida, Gainesville, Florida. And this one particular track of a balloon that I have shown in the on top of satellite image in the upper left of the image here shows the track of the balloon as it progressed over 50 hours, about 2 days, and continued to track with the flow into the circulation of Hurricane Ian. Now, the satellite picture shown is at the end of that 2-day period. The balloon was obviously flying over 2 days, eventually reaching the center of the storm. This was really our first demonstration of flying a balloon of this type into a tropical cyclone. Frankly, we were extremely happy with the way that this worked out. Partly because the balloon had to encounter many things that can be difficult to fly in. One is heavy precipitation. The weight of the water on the balloon can sometimes limit the operational capabilities that we have for flying into different areas, such that if it really gets too heavy, we have to, there's only so much we can do to ascend and descend. But in this case, we were able to take advantage of some of the dry air, but also the capabilities of the balloon to direct the balloon to ascend and utilize more resources, but to keep it aloft and fly into the storm itself. Essentially, the convergence and inflow into the storm was able to guide the balloon towards the center and actually make it into the center as it passed the Florida coast. One of the things, well, what the shown in the bottom here is actually the vertical profile as it flew from about across Florida into the cyclone itself, and the levels that we were flying at. You can see a pretty ragged profile here, unlike some of the smoother profiles shown previously, and that has to do with both the turbulence but also the precipitation within the system, these sharp changes in elevation and in direction of flow. But we were ranging from as low as 200 meters above the surface up to about 7 kilometers above the surface as we flew and eventually got into it. At times measuring winds at about 70 knots at about 800 meters above the surface. It was really a fun storm to demonstrate the capabilities and actually do some direction to ascend and descend and capture and use the winds to propel us into the right direction. During this campaign, for the entire summer, we worked very, very closely with both the National Hurricane Center, the Hurricane Research Division, as well as NOAA's Aircraft Operations Center to assure that we were collecting optimal data along with the aircraft that were flying, but also to assure that we were not conflicting with the aircraft as they flew. We certainly did not want to have any discomfort or any close encounters with the aircraft. So we wanted to work very closely with them, and we did. And during this first demonstration season that we flew in the tropics, we agreed that we would not fly close to the aircraft at all. In fact, we maintain several hundred miles distance between aircraft. And we did that, but as the aircraft stopped flying, as the system passed over land, we were able to take advantage of that and fly into the system. Some of the nice features, if you're really familiar with the development of a tropical cyclone, there's often inflow towards the lower levels, but outflow at the upper levels. And in order to direct the balloon, we're actually able to use those different wind flows. And you can see an example here. On the left-hand side of my path here, we actually made a hard right turn. And that was to deconflict with some of the aircraft that were flying, but we were able to take advantage of the outflow to push ourselves farther away from the storm and then lower down to lower levels and take more advantage of the inflow to push us back towards the storm. So it was kind of a maneuver there that was really beneficial to us to be able to navigate by utilizing the different levels of winds within the tropical cyclone. So that was our fun with Ian, and we can go on to the next slide. I think we're going to finish up here, and I'll say thank you for letting me share the slides, and we can go into some discussion.
Go ahead and unshare the slide, please.
Okay, I was on mute. Fascinating. That's quite an accomplishment for just a few years into the program. Glad to see that it's tied in on the big research projects. It looks like an opportunity to collect some really valuable data that might help with the challenges of rapid intensification. Was that part of what your thinking is? The kind of data you'll be able to gather?
Certainly, in the long run, yes. That rapid intensification is, of course, of interest, both collecting data in the environment surrounding a cyclone and having balloons well in advance of the cyclone, but also hopefully capturing, getting into the cyclone like we did with Ian. We're certainly interested in that for sure. And also the path of the storm as well. I guess one of the things that we believe, anyway, is that given that there are less observations in the central Atlantic and eastern Atlantic, and the aircraft are often unable to fly in those locations because they are so far from North America, it may be a great location that we can add value more so than in other parts of the Atlantic by flying these balloons in that area and collecting observations, not only for rapid intensification out there, but also for track and initial development of the system.
Yeah. I've always kind of looked at the initial development as kind of a subset of the rapid intensification. It's both, but you have to look at some of the same stuff. From a communication standpoint, can you fly multiple balloons at the same time, or is it a one shot at a time?
Absolutely, I can talk through that. There's a massive back end to controlling these systems, but the answer absolutely is many at a time. The peak that we've done right now is 40 concurrent flights, and a lot of this is automated pretty highly. So we have on board, there's code that is configured to execute the flight plan that the system was given. That flight plan gets updated by another set of algorithms that looks at the weather, looks at conditions that are favorable or unfavorable to flight, tries to avoid those, tries to look at where our targets and objectives are, tries to target those, tries to maximize data collection range in the vertical. So it handles all of that trade-off. Generally every hour it then decides what the new flight plan should look like, that flight plan being essentially a range of upper and lower bounds. As I mentioned, the controller chooses when to turn around. So it takes care of that, and we've been implementing some more constellation level control on top of this to say, for instance, as Todd discussed, we have a distinction between this cruise or endurance mode where we stay at high altitude and you can go relatively far and fly for a long time, versus profiling, which is a bit more costly in terms of you can only do a finite number of profiles, but collect valuable data. And so we can at this point now define on a map, this is a region where we care about the data. Please profile over here, and anything that flies in endurance mode will switch to profiling. Once it exits the region, it will go back to high altitude. And so a lot of these decisions are made without a human needing to actively look at it. And so all of that means that we can have just a single person keeping an eye on it while there are dozens and dozens of balloons flying at the same time.
Wow, that's fascinating. I can visualize, back to your other statement about the difficulty in remote in situ sensing when you get out over the open pond, arraying the balloons kind of in a pattern like that we're flying the G4 with dropsons. Only the advantage is you can do this simultaneously, so you get a more synoptic measure of the system out over the Atlantic. Is that kind of what you were thinking for the future?
Absolutely. I think that in all of the campaigns that we've done, our aim is to have many balloons concurrently aloft and spread them out. And so there are generally two ways that you can spread out. Laterally, if you have a wind field that varies, say, more northerly at one altitude, a bit more southerly at another. The other thing that you can do is spread them out in terms of position just along the same trajectory by having faster or slower winds at different altitudes. And so generally there's always a way to get the kind of distribution that we want, which is generally a few hundred kilometers at least between them, so you're not collecting overly redundant data. But indeed the aim is, as you fly, to just collect these large samples in as close to a grid as we can reasonably achieve. And then when there are particular local systems of opportunity, try to navigate towards those and profile them more intensively by choosing when we launch and also redirecting units that are currently aloft to those areas.
Fascinating. Do you get the, I assume you're collecting the data in real time as it's being gathered, it's being transmitted back to you from the balloon?
Yeah, it's close enough to real time. We collect data at relatively high frequency and then transmit it down in packets because you don't want to be talking every 5 seconds. Yeah, the end-to-end latency between getting this data in, doing quality control on it, verification, having it ready and packaged and deliverable right now is I think around half an hour, and we can clean up the back end of it to get that down to around 10 minutes pretty readily, and we're planning to have that in a few months.
Excellent. That I think you guys mentioned earlier in the description that you're still working on the process to ingest this data in real time into the models. How's that going?
Good question. So we are spending a lot of time ingesting not only the tropical data, but also the data that we've collected in the Pacific and Arctic, as mentioned. We are assimilating that into, we have several efforts to try to demonstrate the value of the observations by running what we call data denial experiments, which basically means run one run with and one run without the data, and see if that can happen, if that can provide improved forecasts. Now, we've done some work ourselves with a model called MPAS, which is a model out of the National Center for Atmospheric Research, to assimilate this data into the forecast. And we found that we have found some statistically significant results, although they are frankly relatively small at this point, but we're continuing to push on those. And that means that within a 3-day forecast, for many observations that were collected over the Pacific Ocean, the forecast 3 days later over the United States and North America was improved at different vertical levels in the atmosphere. We tend to look at the mid-levels, which happens to be 500 millibars or so height, to see how much is improved, and we are seeing value there. We're also in the midst of a project with NOAA right now to assimilate this data into the global forecast system in retrospective runs. And we're really looking forward to getting the results from that. Essentially early on in the results, again, from the Pacific campaign that I just mentioned, those results are showing some benefit, certainly some benefit. It's close to statistically significant. We expect that with more observations, we'll be able to show more value. Now, the tropical data that we just talked about will be assimilated again into retrospective runs of the GFS in the coming months, and we'll soon have results from that. As Andrey talked about before, getting more and more balloons into the air at once is something that we really want to do, such that we can have more observations over larger areas, and we expect that having more observations will be more beneficial to the forecast. So work in progress, but there's certainly some good news coming out of that early on right now.
Wow, that is good. Outside of the basic fundamental research that I'm fascinated with, do you have other clients that are interested in this data?
We certainly do. The Department of Defense and Air Force Weather Agency is very interested in this as well. NOAA is interested in it. We are working ourselves to like I said, demonstrate the value of the data, and we do expect that with enough being able to show the value of this data, that we will have more and more interest. Now, our focus up to this point in the history of the company has primarily been in the United States. We do expect that we will have interest from other countries as well as we continue to fly more balloons, and we'll be focusing on that as we move forward.
Cool. When you were showing the sites you launched from, my mind kind of registered on Svalbard. How did you come across Svalbard as your site for launching?
Yeah, that was a fun one. I can talk a little bit. So the aim was to do a launch campaign in the Arctic. This was working with the Navy Research Labs Thin Ice program. So they were aiming. First, we did this in 2021. They wanted to have a whole aircraft and drops on field campaign, but due to COVID restrictions, ultimately ended up canceling all aircraft flights. And so we ended up being the only ones who could get up there and do something. And when you're trying to launch in the Arctic, generally speaking, as you can probably see from looking at the maps of our flights, it's easy to go with the winds around the Earth. It's harder to make significant moves north or south. And so if you're trying to get data in the Arctic, it helps to start as far north as you can. And to cover the region, we also want points that are reasonably well separated in longitude, so that if you can fly halfway around the Arctic from one side, halfway from the other, now you have more or less full coverage. And so one is Northern Alaska. That was a pretty straightforward choice to make, being US-based. And what's opposite Northern Alaska and still very far north? So that's one reason. The other reason is that there's a lot of research already going on in Svalbard. It has a decent amount of infrastructure to support people coming out there and saying, hey, we want to do a bunch of balloon launches. Please give us gas. Please do some logistics. We sent one member of our team, Kai Marshland, was up there for a month and a bit, 2021, and a similar amount of time this past August as well, doing these launches. So I think we had two people overall, one an employee of our company, one as a contractor. This past year we had 3 people. And yeah, it seems the hardest part with Svalbard is firstly getting there yourself, and secondly getting equipment there. Both of those are major undertakings by people in the company. I think on his way back from Svalbard there were 5 different flights to get back to California. So, but once you're there, it's a very effective site to operate from. And we're looking into setting up long-term operations there that will be on a more permanent basis in the coming years.
Wow. Yeah, I was stationed in Iceland, and we had a little placard in the weather office in Iceland that said, don't feel bad, it could be worse, you might be stationed in Svalbard. That kind of reminded me, we had challenges launching the radiosondes there in Iceland due to really high wind conditions at the surface. What are your weather limits as far as launching the balloons?
That's a very good question. It's something that we've been trying to push. The design of the launch equipment is something I've been responsible for over the past few years. And really the question is less what the balloon hardware itself can handle and more how you can manage it so that you release it safely. So if you think about inflating a relatively... these balloons aren't enormous. As I mentioned, our focus is on lightweight, but they still have a decent sail area, and so when it starts gusting 20 knots, it's hard to keep this thing vertical. It will definitely be blown sideways, and if there's something in the way or if there's enough turbulence that you hit the ground, suddenly it's not looking like a viable launch anymore. And so a lot of the design effort goes into, well, how do we design a rig that's easy to load this into and then hold it in such a way that when it's buffeted by wind, you can still do the inflation and release without hitting the ground, hitting any nearby obstructions, or just overstressing any parts of the hardware. So right now our limit is in the 10 to 15 mile an hour winds that we can handle reasonably, and then 20 probably with best execution and all of the equipment functioning as intended. We're going to be continuing to push that as time goes on. I think there are some pretty promising avenues to get us above 20 miles an hour comfortably, which is beyond what we're comfortable with at the moment, definitely. And the other challenge is rain, which we've also first started actually operating in this tropical season. The flight hardware itself is waterproof. It needs to be to deal with the situations it can encounter. The launch equipment was less so, because we weren't expecting the hardware to be as waterproof as it was. And so we're working through getting it a bit more reliable there. Those are some very easy fixes, fortunately. So that's another thing that we've been trying to push on, is having more capability to launch in all weather, as close to all weather conditions as possible. I still don't recommend it during a thunderstorm on a flat plane.
Yeah, I think the highest wind I remember us getting a successful launch in Keflavik was about 45 knots. And, well, they smartly raised the ground that they put the inflation shelter on, so that you got a little bit of a slope running away, because it would go immediately sideways when you open the shelter door, and it would keep it from bouncing on you. So that still sounds like that's going to be a challenge operating in the Arctic, where low winds not always that easy to come by.
Oh yeah, the good thing about it, though, is, as I mentioned, because we have a decent amount of control post-launch, what we've been doing is, when there's a good window, we can launch 10 of them, and we have peaked in the Arctic at launching 10 of them in one day. And then over the next few days, they'll spread out and cover completely different regions of the Arctic. And so all it means is that essentially for the first few days of flight, they're close together and the data's a bit redundant, but we're spreading them out. And then from that point on, you're still collecting a lot of observations. And so there can be a bit of a delay in that sense, but if every 3 days you're launching 10 and then spreading them out, then what that turns into is relatively uniform coverage nonetheless. So we play games like that.
Yeah, you don't have the small windows where you actually have to launch at a specific time. You're in good shape for. I didn't think about that. Let's see.
Makes life easier.
Hey Tim, I've been ignoring you. What you got on your end?
We've got some good questions coming in from online, and you showed a slide briefly that mentioned permissions of places you can go and places you can't. What's the situation on that? You can fly them around the world. Are there any flight restrictions?
Yeah, so essentially these systems are so lightweight that under FAA and ICAO regulations, they don't really have any strict operating restrictions. The provisions that are stated there is one needs to get approval from the launch country. And generally speaking, when you're looking at FAA regulations, there's always a clause that says that you shouldn't create undue hazard, which is a very important thing. We don't want to say, oh, we're lightweight and you're not technically regulating us, let's launch at the end of a runway. So for obvious reasons, we coordinate, especially on launch, we tend to coordinate with nearby airfields and towers. And then in flight, we wouldn't, say, fly at approach altitudes at low levels over a busy airport when we're going across the world. But generally speaking, because these things are considered so lightweight, there's little overhead to airspace coordination. I remember when this was a student group, we got our first transatlantic flight when we were getting into French airspace. And so we found someone who spoke French, tried to get them to call the tower. And they called the tower. The first question was, how heavy is it? We told them. The response was, never call us again. And as we develop the technology, the goal is to continue making these things smaller and lighter. As I mentioned, we've done about an order of magnitude reduction over the past 5 years or so, and we can push close to another order of magnitude out of that over time as well. And so you get into something that becomes very, very small and lightweight, and the way that aviation regulations are set up. They essentially understand that they can't control a lot of small lightweight objects in the world known as birds, most of them very small birds, and so we're looking to operate in that scale. And still, the other thing is that we have real-time position data on all of this. So one thing we've talked about with the FAA is we have given them access to real-time positions and altitudes of all of our balloons. To our best understanding, they don't actively look at it. But this information is available, and perhaps as drone technology also gets wider adoption in the world, and people develop more systems to handle large numbers of small objects in the atmosphere through that whole side of the world, then air traffic regulations will catch up in ways that can better assimilate this kind of position data and take advantage of it. But yeah, our goal is to work closely with the relevant agencies and coordinate all of these flights.
Let me ask an Elon Musk type question. This question comes from Casper, but I'm moving it over to an Elon realm. His whole thing is recover, refuel, reuse. Is that something that you're able to do yet? Recover, reuse?
That's a great question. Most of the time, we are not able to recover it because either it lands in the ocean or it lands somewhere where it's simply not effective to get someone to go out. We don't have that many volunteers looking to hike the Mongolian steppe right now to try to get some of them back. But it is a very relevant question, and I think it becomes much, much more applicable as the endurance of these systems goes up. So I've talked about weight reduction. The other thing that we've been continuously pushing on is performance improvements. So our record endurance was on the order of 5 days back when we were doing this as a student project before we started the company. Now our average is well above 5 days, and our record is going into beyond 2 weeks at this point. And there's room to push that further quite a lot as well. And once you get out into something that is capable of circumnavigating multiple times, you can say, well, we know this flight is getting close to its operational limit. We are currently flying over the US. Let's target a designated recovery area that might be some farmers' fields that we have a relationship with along the East Coast, for instance. And we'll land it there, we'll go out, recover them, and then you can talk about reuse more. There's components that do and don't survive landing. For instance, the balloon envelope isn't going to be reusable regardless, because the moment you land it and there's a tree nearby, that's no longer something that you can try to use again. But much of the avionics systems, the sensors is a tricky one. Some things are okay, some things are pretty delicate. You don't really want to deal with a humidity sensor that's been in the mud, for instance. But there's definitely an argument for it, especially as the endurance gets longer.
And a follow-up on that is there any place that we, the public, can view the data that's coming in? Is that available online in any place yet?
So right now, most of the data viewers are set up on a user account and request basis, and so generally people we work with, all the way from meteorological agencies and to launch contractors who operate these balloons, we give access to our internal data viewers. So that's something where we are more than happy to coordinate with people on a individual basis. There's no overall fully public viewer of all these systems at the moment, but we'll see how that evolves over time.
Peter Black's asking, what about the biodegradability of the systems after landing? It's a good question.
That's a great question. So right now, it's fairly limited. What we have been doing as a company is purchasing plastic offsets to, I think with around a 2x margin, offset the amount of material that we're putting out into the environment. And that amount is also comparatively small. If you, as one of the team members who was looking into this found out, it's hard to find a plastic offset company that cares about dealing with the quantities of waste that we're producing, because it barely tips the needle from their point of view compared to what they're used to seeing. But that's the way that we're approaching right now. In the long run, there's two approaches. One is obviously the more you reduce the weight and increase the performance, the less waste there is per unit data collected. And those are both things that we are working hard to optimize, and I think there's a lot of room to go beyond that. And already compared to radiosondes, there's a pretty big advantage in terms of waste per data point collected. But the other thing is a lot of the mechanics on the system can definitely be set up to be degradable. The balloon envelope itself is a more challenging one because you have to deal with pretty harsh environments. And so you need it to not break down due to UV, for instance. You need it to not break down due to prolonged exposure to moisture. You need it to have relatively good mechanical strength. And so those sorts of things get challenging to optimize, but I think that there's still a lot of potential. And recovery is the other thing that comes in, because in the longer term vision, when we are able to recover these things more reliably, then whether or not you can refly it, that's waste that's no longer going into the environment. So it's a very good
answer.
question.
One couple of other comments from Peter, and then then these are just comments, but he's talking about a couple of events that you flew into when you were off of Cabo Verde in the tropical depression AL97 as it began moving across the Atlantic, and he also talks about flying balloons into the Earl outflow circulation. Anything in those two specific instances that you want to touch on? A couple of very specific storms.
Sure, yeah, I can talk on that. Essentially, we really had our first exciting venture in the tropics when we got going with the AL97 system. That was a Cape Verde system that was moving westward through the Atlantic and had the potential to develop into a tropical cyclone. It did not really fully develop into even a depression, although it was marginally on the edge of a depression, but it had that potential. And we were able to get we flew several balloons in and near the system. At one point, we had 4 balloons that were very near the system, 3 to the north and 1 in what you would consider where the center would have been had it really turned into a depression. At the same time, the NOAA aircraft, the NOAA G4 aircraft was flying and dropping sondes into the system, so we were able to compare, and Pete was able to see this data, the comparison between the drop sondes and the Windborne observations, the Windborne vertical profiles that were collected with the balloon. The great thing was we're getting very similar data, which of course is good. We don't want to be redundant, but in this case, the value was there because we were well out into the eastern Atlantic Ocean, somewhere where the aircraft rarely flies. In this case, they had a special experiment to demonstrate flying out of Cabo Verde. We were able to collect data at the same time and show that we were able to collect similar data. So that was really, really exciting. For Earl, it's that spent quite a long time in the Atlantic as it moved northward in the, west central Atlantic, past north of Puerto Rico and up into the further north in the Atlantic. We had several balloons fly, launch from Puerto Rico and fly in and near, or I should say near Earl, and in the outflow. We were able to capture much of the outflow around the system and actually circle the system in some ways with some of the balloons. So in that case, collected a lot of environmental data around the system and some of the direct outflow winds that were associated with the system. So yeah, two exciting events that went along with Ian this summer. So so it was quite a successful season for us, and we really enjoyed getting in there and hope to demonstrate that and be able to collect similar and even more data in future tropical seasons.
You're muted, Tim.
Again, sorry, Bill, this has been terrific, guys. This has been absolutely amazing. It's coming up on the top of the hour, so we need to wrap up. But Bill, jump back in. Any final questions and thoughts?
I do. I was thinking about when you're operating a balloon, how far out in advance do you try to plan to execute maneuvers to change what the balloon does?
That's a great question.
That's a very good one. So generally speaking, it depends what we're looking for. There are some decisions that are made many days in advance. For instance, we know which rough domain we want to target, and so that's somewhere where we can set for the optimizer a target point that is maybe easily 4 days ahead of time and go towards that general region. Profiling decisions are probably made closer to a 24-hour cycle. And Todd, I'm sure, can weigh in as being someone who's made a lot of those decisions operationally. But it's pretty flexible. And sometimes when we come into something that is a new discovery that we notice is potentially interesting, we can turn the balloon around within half an hour and say, okay, let's go down and take a look at this, for instance.
Fantastic. You guys, this is just a fantastic opportunity to learn about some new technology. I really admire what you guys are doing and look forward to seeing how it advances in the future.
Thank you very much.
Thank you. Thank you. Really appreciate the opportunity to talk here, and we really are looking forward to the future as well.
It's been a fast hour, gentlemen. That's a quick hour. That's a lot of great information. I just love what you're doing. Let me ask one last question. What is the future? Where are we headed? Either one. What's your next step?
Yes, so the next step from us is to really scale up our ability to manufacture, operate, launch these systems and collect data. What we're looking for, we've been doing some small-scale campaigns where we launch, as Todd mentioned, maybe 80 balloons, maybe 50, depends what we're looking at, over the span of a few weeks to a couple months. We want to switch to year-round operation. We want to start setting up permanent sites, and we want to increase our launch cadence so that we're generating a much more significant amount of data. And what we're talking about is going into the hundreds of profiles per day regime so that we're operating a scale where we can make a significant dent in the global observing system, if you will, and hopefully see some impact out of that. And overall, we want to improve operational forecasts.
Well, congratulations. A job well done so far. Look forward to seeing what's coming out in the future. Gentlemen, thank you. Really appreciate it, Todd, Andrey. A great program today, and we look forward to having you back to hear how much progress we're making toward those ends. So thank you so much. We appreciate it. Bill Reed, thank you. Bill, thanks for being with us as always, former director of the National Hurricane Center, with great insight and great questions. We appreciate all you do for us, Bill, as well. Of course, thanks to our sponsors who make these programs a possibility. USAA, the South Padre Island Convention and Visitors Bureau, the Weather Company, Weatherboy, Walmart, City of Brownsville, Blackmagic Design, the Port of Brownsville, all part of this program. You see some of them on your screen as well. Live view, a big part of what we're doing as well. So thanks to each and every one of them. Of course, the National Tropical Weather Conference, we are back in person April of 2023 on South Padre Island. You can register now. Early registration is open on our website and on Facebook as well. Click the link and follow the way. We'll be at the Marriott Courtyard Hotel on South Padre Island in April. That's it for today. We appreciate you being with us today. Have a great rest of the week, and let's get through the rest of this hurricane season on a quiet note, okay? Thanks for being with us. Take care. Have a great week.